Thank you. Thank all the organizers for inviting me. And I'll tell you a little bit about some of the work that I and my students have been doing over the past few years. Right, so preparing our students for Quantum 2.0, there's a couple of sort of two halves to this talk, and I'll start with this part, right? Quantum 2.0. What do I mean by that? Right, well, before we talk about 2.0, we should talk about 1.0. And I think of Quantum 1.0 as the quantum mechanics of the 20th century, right? The quantum mechanics of Schrödinger and Heisenberg and Dirac, right? And it allowed us to understand and explain all of this stuff here, right? Arguably the most accurate physical theory ever predicted, right? Ever formulated, 14 decimal places of precision in some places, right? Truly an amazing accomplishment, right? And it led to sort of these types of technologies, right? Modern semiconductor industry, the transistor, lasers, CCD cameras, right? All came out of our understanding of quantum mechanics. Quantum 2.0, I think of as the quantum mechanics of the 21st century. And it's not different, right? The theory is the same, but we're just looking at sort of different aspects of the theory that we haven't really focused on before. And I think that there are kind of two distinguishing characteristics of it. And the first is that it's based on the behavior of individual quanta. So for example, the laser, right? Quantum mechanical phenomena, lots of photons, right? Quantum 2.0 technologies are based on single photons, right? Transistor, lots of electrons. Quantum 2.0 transistors are single electron transistors. So that's one distinguishing feature. And another is that we're kind of moving beyond understanding and explaining the world and really down to the level of controlling and engineering things around us at kind of the nanoscale. So a couple of examples. Right, so Quantum 1.0, we could explain the periodic table. Predict spectra, you know, we could understand how it goes. But if you wanted a light emitter at a particular wavelength, you had to find an atom that had an emission line at that wavelength. In Quantum 2.0, we're going to design our own atoms that have properties that we want. So for example, this shows quantum dots, right? You can see fluorescence here at a lot of different colors. But this is all the same material. The only thing I've done is change the size. So these are these nanoscopic three-dimensional quantum dots. And if I control the size on the nanometer scale, I can control the wavelength that they emit. And this is really important because this is all the same material. Cadmium solenoid, it's semiconducting material, all the same material, so all the processing that's involved in doing it is all the same, right? So you can kind of manufacture these things much more easily. And so here's an example of where this is being used now. Latest generation of HD TVs use quantum dots for their color spectrum. Okay? So that's Quantum 2.0 technology. Another one, quantum cryptography. Right? You want to send your information to someplace, right? So your credit card, and you want it to be secure. And in order to do that, you have to exchange a secret key with the person you're trying to send this message to. And that key is basically just a series of random ones and zeros. And the most important thing is that nobody else has a copy. You have a copy, and the person you want it to has a copy, but somebody in the middle doesn't also have a copy. And quantum mechanics solves that problem, right? So that's a hard problem. Classically, you never know how secure your message is using classical physics. But in quantum mechanics, we have what's called the no-cloning theorem, which says that you cannot make a perfect copy of an individual quantum system. So that says if I have a copy and I send it to Eve, or sorry, I don't want to send it to Eve. I want to send it to Amazon, right? But Eve can't get a copy. The eavesdropper, Eve is the eavesdropper, can't get a copy of that message, right? Because the no-cloning theorem doesn't allow it. So it's security based on the laws of quantum physics, okay? And these systems exist. You can buy them off the shelf now. You can buy quantum key distribution systems. So you've probably all heard about Google's quantum supremacy. that Google has built a quantum computer that could do a calculation that would have taken, one of the world's largest computers 10,000 years to do. And there's some debate about whether how supreme that was. But I want to give you a different example. And since this is an optics conference, I want to give you an optics example. And I think this blows Google out of the water. This is way more quantum supremacy than Google ever did. And it's this notion of boson sampling, right? And photons are bosons. So here's the basic idea. I have sources that emit single photons. Okay, so in this case, I have 3 single photon sources, and I send it into this array. And this basically is just an array of interferometers, right? There's mirrors here, there's beam splitters, looks like a big giant array of Mach-Zehnder interferometers. And then they come out, and in this case, there's 7 detectors here. So this particular implementation has 3 input modes and 7 output modes. And the question is, what are the probabilities that I will detect those photons at any of these detectors? Okay, relatively simple question. It turns out, though, that if the number of inputs and the number of outputs gets large, the solution to this problem scales exponentially with the number of inputs and outputs. And the world's largest classical computer couldn't calculate what the results would be. Okay? And you might say, well, that's just kind of a toy example. Who wants to know where bosons are going to go inside this interferometer? But it turns out that this is related to 2 other problems. It's related to calculating a matrix permanent, which is kind of like a matrix determinant, but it's a similar kind of thing, but it's a known problem that's known to be hard in mathematics. And it's also related to calculations of vibrational spectra of molecules. So if you build a big enough one of these, you could actually imagine doing actual quantum simulations of molecular motion. Okay? So that's the idea. And people have been doing this for a little while with a few photons, and this is the first really large-scale implementation. This just came out a couple of weeks ago. Okay? And so what's the idea? So what do we start with? So we start with a high-purity single photon source. Individual photons at a repetition rate of 76 megahertz coming out in a stream, single source. And then you demultiplex them. People who know some optics here, each one of these things is a Pockle cell, right? And so timing this thing and getting it all to go is quite an endeavor. And so you take this stream of photons and you demultiplex it into 20 parallel photons. And then you couple it into this interferometer here that's got 20 input modes and 60 output modes. Okay? And these 60 output modes are superconducting nanowire detectors that have to be maintained at cryogenic temperature. So you got 60 of those. Okay? And the Hilbert space of dimension of this thing is 10 to the 14th. Okay? So calculating this on a classical computer is just not going to happen. Okay? So the results of this experiment, nobody is going to do. And I want to show you kind of what it looks like. So the source is not on this picture. The demultiplexer is not on this picture. The detectors are not on this picture. This is just the interferometer. Okay? And so, and all of you who've done optical alignment, imagine aligning this thing. Okay? So the photons come out, right? So the photons are all in single mode fibers. And the interferometer is actually free space. So this here, where it says 20 input modes, these are 20 single mode fiber couplers, and the photons that come out of these 20 single mode fibers. They go into this interferometer, right? This is the interferometer, okay? And it's actually kind of like, it's a 3-dimensional thing. It's got these stacks of glass, and there's like 10 layers of 6 modes, or I'm not exactly sure on exactly the details of the interferometer. But the interferometer is here. And then you've got to go out to 60 superconducting detectors, and that's this. Around the side here these are single mode fiber couplers. You couple all of those 60 modes back into individual single mode fibers, and then send the whole thing off to these superconducting detectors, right? I don't know how many years of graduate student time went into actually aligning this thing. It's unbelievable. Okay. So those are kinds of examples of things that you can do with this, what I call quantum 2.0 technology. And so now let's move on to the second part, and let's talk about preparing our students. Okay? And I'm talking about teaching quantum mechanics here. And now the students might think this, oh, okay, I'm talking to the faculty and a member here, and that you students can all kind of zone out. But let me suggest that you pay attention, and then when you go back to your home institution, you can go up to your quantum mechanics instructor and say, there's this guy at Reed College that says, this is the way we should be teaching quantum mechanics, and you're not teaching it that way. Why not? And I guarantee you that they will be really pleased to hear that from you. Okay? So pay attention. So what do I think? So I'm talking mostly about undergraduate, junior, senior level quantum mechanics. And I would say that why don't we place an emphasis on two-state systems? Photon polarization, spin 1/2, right? What are known in the language of qubits, quantum bits, simple two-state systems. The simplest quantum systems that you can imagine, okay? And we can talk all about this. And we're going to spend a lot of time talking about the behavior of really simple systems and elucidate a lot of important quantum mechanical principles. And they really connect well with this notion of quantum 2.0, and we can talk about entanglement and quantum information and computing and all this kind of stuff. And why not do this with the simplest systems that we know how to do? But that's not all of quantum mechanics, right? You can't just end with qubits. You need to move on, right? But after you've done this, then you move on to sort of n-dimensional discrete systems, continuous wave systems, wave mechanics, hydrogen atoms, etc. But do this after you've done sort of the easy stuff, but still a huge amount of quantum physics that you can get out of those relatively simple systems. Okay? And I'm not the only one that thinks this. There are a number of books that kind of take this approach. In particular, this book by John Townsend has been around for 25 years. It kind of takes this basic approach. And in some shameless self-promotion, that's my book. And the nice thing about this approach as well is that in addition to talking about the physics, we can actually do the experiments. In teaching labs, we can do experiments that really explore these kind of fundamental physics principles, right? So these are a bunch of experiments that I and my students and others have developed that involve these sorts of things. And they're all basically quantum optics experiments based on single photons and photon pairs. And the first 5 of these are described as appendices in my book. And then these are a couple that have come later that other people have worked on. And so I'd like to kind of give you a flavor for what are these labs, what kind of labs can you do, right? So I call it proving photons exist. So what do I mean by that? Well, for a long time we've been telling our students that the photoelectric effect proves that photons exist and that light is made of photons. And when we do that, we're lying, okay? Because you can completely explain 100% of the photoelectric effect assuming that light is a classical electromagnetic wave that's incident on a quantum mechanical detector, okay? And so what the photoelectric effect proves is that electrons are quantized. It doesn't tell us anything about the quantization of the field. So I want to do an experiment in which I absolutely need to use a quantum description of the field in order to explain it. Okay? And if we do that, that's what I mean by proving that light is made of photons. So the idea here is, what do? You take a single photon, you send it onto a beam splitter. I can detect it here at T. I can detect it here at R. But I can't do both, right? A single photon can get detected at one or the other, not both. And in particular, if I have a kind of a regular stream of photons, I should never see coincidences between those two detectors, okay? And in the words of Philippe Granger, who was the first person to do this experiment back in the 80s, single photon can only be detected once. That's kind of what we mean by a photon. So how do we see this effect? Well, the first thing to know is that attenuating a classical light source does not give you a single photon, right? And so even though laser is a quantum technology, the light that it produces is actually in some sense the most classical light you could imagine. And if you attenuate a laser so that it's on average 1 photon, or even on average less than 1 photon, you will not see this effect. There are always some probability. It's a Poissonian light source. There's always some possibility of having 2. And so we really want 1 and only 1. And the way we do it is this process called spontaneous parametric down conversion. And we take an intense laser beam and we shine it onto a nonlinear material. And there's a very small, like 1 in 10 to the 13th probability that one of those photons in that laser beam will get converted into 2 other photons. So this is known as the pump photon. These are called the signal and the idler. And of course, that process has to conserve energy. And that also means that the frequencies of these have to add up. It has to conserve momentum. And so if I know the direction of that photon goes in, I know that the direction of the other photon goes in. And they're always produced at the same time. And so how do I use 2 photons to make 1 photon? Well, what I do is I put a detector over here, and when it goes click, that detection projects this other beam into a state which has exactly 1 photon in it. And I know where that photon's going, and I know when it's going to get there, and now I can do my single photon experiments over here. And so what do? We then send that photon onto this beam splitter, and we look for this lack of coincidences on these 2 detectors conditioned upon the presence of that photon over there. Okay? And so here are some results, right? So these are results from student teaching lab. I don't have, what are we actually measuring is this quantity called G2. It's the degree of second order coherence. It's related to this coincidence detection. It's a correlation function between the outputs. And I don't have time to prove it. It's not that hard to prove. But for classical waves, G2 has got to be greater than or equal to 1. Whereas if you have a true single photon input, you will get G2 is equal to 0. And anything less than 1 is a sign of a quantum mechanical field that cannot be explained by classical electrodynamics. And here are some results from the teaching lab. We see G2s that are significantly lower than 1. This column here tells you how many standard deviations that number is below 1, right? So we can get 150 standard deviations away from this classical physics limit. Highly non-classical fields, really relatively pure single photon states that we can then do other experiments with. And so, for example, if you have a single photon, what's the coolest thing that you could imagine doing with it? Well, right, so this is the experiment that we did. And now I'm going to take that single photon, I'm going to send it into an interferometer, and I'm going to show that I can take a single photon. That single photon takes 2 paths through this interferometer, will interfere with itself. And then, oh, by the way, I have these 2 detectors here that monitor the 2 outputs. So I can simultaneously look for a lack of coincidences here and show categorically that, yes, I get interference and with truly a single photon all at one time. And so here's that data, right? So this is single photon interference, high visibility. We scan that interferometer. We get lots of nice high visibility interference. That's the wave-like nature of these photons. Oh, and here's this G2 thing, and we see that everywhere in here it's less than 1. And so, yes, indeed, I truly did have a single photon in that interferometer, and I'm seeing both the wave-like and the particle-like nature of this photon. So that's a pretty cool experiment. Okay, so what's next? So like I said, all the experiments we've talked about so far are single photons, 2 photons, right? That's what we've done in teaching labs. But now the sort of the research community has got 20 photon sources. We want to push up, right? We want to make some more photons. So let's see if we can make 4, right? Photons come in pairs, right? So we'll start with this source, right? So again, spontaneous parametric down conversion. We make 2 photons. This is a slightly different source. Rather than separating them by their momenta, we're going to separate them by their polarization. So the 2 photons have orthogonal polarizations, and I can just split them on a polarizing beam splitter. If you want 4 photons, you just do it twice. Okay. But what's the problem with this? The problem is that these 2 photons come at the same time, and these 2 photons come at the same time, but these 2 don't necessarily come at the same time as those 2. And the actual emission process is random. And so if you pump this with CW laser beams, the probability that those two and those two will occur at the same time is vanishingly small. So we need to synchronize these two sources. So we've got a short pulse laser. So we start out with 50 femtosecond pulses at a repetition rate of 80 megahertz. And now again, so now that the photons can only be produced in this window, and they don't always produce photons at the same time, but sometimes they do. And when they do, they're synchronized to within 50 femtoseconds. So that's good enough for us. So we start with 80 megahertz. Each of these sources produces pairs at a rate of about 10 kilohertz. That's our kind of biphoton rate. And then if you look at the rate of 4-photon production, we're at about 1 hertz at the moment. So this was an experiment done in my lab this summer by Amelia, who's in the audience here. We think we can push that to about 10 hertz. Okay, that's where we're hoping to go. So if we can make 4 photons, well, what do we want to do? Well, remember that boson sampling experiment. You need to be able to interfere these photons. And you want to be able to show that I can interfere photons from independent sources. Right? These sources are not locked to each other in any kind of way, and I want to get interference between independent photons. So I'm going to shine them on a beam splitter, and I'm going to put a time delay in here so I can line them up and see how it works. Okay. And so, well, what can happen? So I have 2 photons coming into a beam splitter, and there are 2 ways that each photon can go, and so there are 4 total possibilities, right? I can get 2 photons that go to that detector, 2 photons that go to that detector, and then 2 different ways that I can get 1 photon going to each detector. They can both reflect, they can both transmit. In this case, since everything is timed, I would see coincidences. So these 2 processes lead to coincidences between these 2 detectors. So let's just look at those 2. So I'm going to get a coincidence. What's the probability that I'm going to get a coincidence? Well, Richard Feynman told us that if you have 2 possibilities to get the same result, in quantum mechanics we have to add the probability amplitudes for these things to happen. We don't add probabilities, we add the probability amplitudes, and then we square it. And so we need to add these possibilities together. So we want to do that. But it turns out that this process in particular, where we get this reflection, picks up a pi phase shift. So when I add those 2 things together, they cancel out. That can't happen. So what am I left with? What I'm left with is 2 photons go to that detector, or 2 photons go to that detector, but I never see coincidences. 1 photon never goes to each one. Shouldn't happen. Okay? And so that's what we're trying to do. This is not our data. Eli, who's my other student that's here, is working on this experiment now. And so the idea is, if these 2 photons arrive at the same time, so the time delay between them is 0, this is kind of measuring these coincidences, right? You see that there's a minimum there. You don't see those coincidences. But if you delay them in time and the photons don't get to the beam splitter at the same time, they don't interfere, they don't affect each other, and then you see coincidences. And let me point out that this is not normal interference, right? This is not interference of waves. Right? Because interference of waves occurs on a scale of a wavelength, and it oscillates up and down. This scale you see is not wavelength. Okay? This scale is like the pulse duration of this photon. This is the interference of the photons, not the interference of the underlying waves. And you cannot explain this data using a wave theory. This is an inherently quantum phenomenon. Okay, so in summary, quantum 2.0, like I said, the physics is the same, but we're just looking at it in a different kind of way, driving all kinds of new technologies. And I'd like to say that physicists can kind of take advantage of this. We're kind of really blurring these lines of, physics and engineering. Quantum engineer is now a thing, okay? And for the students out there, right, if you learn this stuff, you will be employable. Okay, and like I said to the faculty, right, it can really inform how we teach, right? There's some really, really interesting physics in these really simple two-state systems, and we can also do laboratories that kind of explore this behavior. So I'd like to encourage people to do that. And then finally, of course, I have to thank everybody else that helped this, right? So a number of faculty at different institutions, a whole bunch of students over the years at both Whitman College and Reed College, and then, of course, support that makes it all work. All right, thanks very much.
Thanks for having me here, and thanks to the folks who worked hard to organize this event. I think it's a really positive experience. I'm glad for your efforts. Yesterday there was some talk about careers, and I just wanted to take a second to echo a comment I heard that I thought was spot on, at least in my limited career so far, which is that you should get a very broad education because you don't know what problems you're going to be working on later. And actually, even though I'm only in my mid-30s, I'm now on my 5th job since my PhD. I've bounced around a lot. There was also a comment yesterday about working in science can be a lot of fun, and you get to meet a lot of great people. And that's been the case for me, too. I don't keep moving because I don't like the people I work with, but just because new things come along. So up until last year, I was working in Albuquerque for the Air Force, doing some project management with them. And yesterday, Professor Maffei showed these beautiful pictures of Albuquerque that made my heart hurt because I have to go back to Minnesota for 4 more months. It's those April snows that really kill you. Anyway, I shall move on. Bethel's a small college in Minnesota, undergraduate college. We actually have been getting about 30 physics grads per year, which is quite large for a undergrad-only university. The way we do it is everyone comes in saying they want to do engineering, and we say, that's great, you can do that here. And we switch them to physics. But actually that turned out to stop working as of a couple years ago. And so we now offer engineering degrees within our department. It's all one department. And that's a wonderful way to recruit students. Every high school parent knows they want their kid to do engineering, even if they don't know what that is. The perhaps drawback for me, I teach quantum mechanics, optics, and lasers, and we can already see the enrollment kind of plummeting in those classes. So I have to maybe up my recruiting game a little bit. But the one good thing is we do have our electrical engineers take optics, and so as we all know, optics is quite multidisciplinary, and that seems appropriate. So I'll soon be probably spending most of my time teaching engineers, which I'm okay with. So I want to talk to you today about spectroscopy. This is kind of the only thing I've ever done in life. You all know that spectroscopy played a key role in development of quantum theory, quantum 1.0 as it was called, right? Bohr kind of famously came along and explained the spectra that were very precisely measured, but up until then hadn't really been understood. And somewhat later, the Lamb shift provided an early confirmation of QED in the kind of late 40s. A couple things to tell you about how powerful spectroscopy can be. Here's a couple examples. One is the case of the hydrogen 1s to 2s transition. You can actually pretty precisely calculate the energy levels of hydrogen. That's mostly true. You need to know 2 things. One would be the Rydberg constant. The Rydberg constant kind of serves as a scale factor. We need to understand how to get from energy into frequency, and frequency is defined by cesium clocks, not hydrogen, right? The other thing you need to know is the proton radius. This is a little bit curious, but it turns out there's always a chance that the electron, as it's buzzing around the nucleus, could actually go inside the proton. And when it does that, it doesn't feel the full charge of the proton, which temporarily, of course, would change its energy level, or on average, we would measure a different energy level spacing. So the other way to look at it is you can use a hydrogen atom to determine the proton radius. People have been doing that, and then about a decade ago, someone tried it with muonic hydrogen. Randolph Pohl in Germany led this effort. And with muonic hydrogen, they got a quite different answer. A muon is 200 times heavier than an electron, so it orbits much closer. And it, of course, can really see the structure of the proton, as opposed to being so far out like the electron is. So then the question was, so did we find some new physics here, or is it just, maybe a little bit of a mistake in the experiment? And we're all kind of waiting with bated breath, but I think this is as of November. This is the most up-to-date status. So they had originally measured the proton radius to be 0.88 femtometers. This is based on hydrogen. The hydrogen frequency experiments are unbelievably precise. So those experiments were done right, but it's just not very sensitive to the proton radius, so you get kind of a big error bar. And then they came along and did muonic hydrogen in 2010 and 2013, and it's quite a bit different. And we've since had some nuclear physics people redo their work, and they got a number that agrees with muonic hydrogen, and another result last fall, I think looking at a different way of looking at hydrogen energy levels. So this still hasn't quite been settled, but it looks like maybe there won't be new physics after all, which is either good or bad. I don't know. But you can see the power of spectroscopy here. Another case, this is from my PhD. Yesterday, Zach put up a picture of my clock. It was the one with the red, blue, green, and yellow light all in it. And that's a fine picture. I guess, people like colors. But I really like this picture. And let me tell you a little bit what this plot is showing you. I can't really tell you how the clock works just because in the interest of time, but we have a way of very, very precisely measuring energy levels. In this case, it's in the ytterbium atom. And we take a laser and we sweep its frequency. And as we do so, we see something happen here. This tells us that we found the resonance. And we found it to within a width of about 1 hertz. Okay? And that means that the interaction between the laser and the atom was coherent for about 1 second, 1/1 hertz. And a second might not sound like a long time, but I think if you were an electron orbiting a nucleus, you would think it was an awfully long time. And if you've taken an E&M class, you might have remembered talking about the quality factor of a resonance, which is the resonant frequency divided by its kind of characteristic width or dephasing time. And in this case, our quality factor was approaching 10 to the 15, which means that this resonator underwent 10 to the 15 oscillations before it got out of step. That's a pretty big number. And it was, at the time of my PhD, which is now about 8 years ago, it was one of the highest level of demonstrations of interaction between light and matter. I think it's now been surpassed by a factor of a few by successive folks. So this is an optical clock, and it's really one of the most precise instruments humans have ever made. Oh, wrong way. So I also want to talk to you about laser spectroscopy, and given that I work at a small college where we primarily teach, I think of laser spectroscopy as a powerful teaching tool. So in a lab where we would do laser spectroscopy, we give students a chance to kind of visualize atomic structure. This would typically be done in the gas phase. Solids and liquids have very strong interactions between them, and you don't recover the familiar energy levels that you would have understood from modern physics. You get to tune a laser, which oftentimes does not work. Tuning lasers can be really painful, and despite having spent my entire career working with lasers, I still don't really like them. But this is a picture of a home-built external cavity diode laser, which is a typical tunable laser that an atomic spectroscopist might build. The diode laser is mounted in there inside of this copper heatsink to control its temperature, a collimating lens, and it bounces off a grating. And the grating is really the key point here because it's able to pick out one wavelength, or a small band of wavelengths, and couple them back into the laser to form, and that's the external cavity part. Tuning the grating then tunes the wavelength of the laser. And it can all be done, of course, on a pretty slim budget. Nothing I'm showing you there is at all expensive. Other opportunities would be to use signal processing electronics. Students can kind of ponder signal-to-noise sources and the overall precision. And then if you want, you could make it a feedback controls lab, have them close a loop, and lock the laser to the atomic transition. Sounds great, but there's kind of a problem, which is the Doppler effect. You all know the Doppler effect. It's the same one as we hear when the ambulance drives by fast, right? The Doppler shift for an atom, you can write it as the dot product of the k vector of the laser and the velocity vector of the atom. If all the atoms had the same velocity vector, that wouldn't be a problem, but of course they don't. They're distributed according to the Maxwell-Boltzmann equation, and a sort of characteristic width, or like the RMS spread of the velocity, is something like That B is supposed to be a subscript. So the Boltzmann constant times the temperature divided by the mass gives you a velocity. And the net result is you end up with what should have looked like this, a sharp, strong intensity pattern as a function of the laser frequency is smeared out. Something like a gigahertz wide, depends on the mass of the laser, of the atom primarily. And because it's an inhomogeneous process, the signal gets very small as you do this. So that's kind of disappointing, but fortunately atomic physics wasn't stuck with this. By my tabulation, we have something like 3 or 4 ways of overcoming the Doppler effect. And actually, in our lab at Bethel, we have all of these. So I'm just going to tell you a little bit about them. The first thing you could do is control the velocity of the atoms by making an atomic beam and intentionally zero out the dot product to make the whole thing orthogonal. The next thing you could do is take a vapor cell. The atoms kind of buzz around everywhere, of course, but using counter-propagating beams, the Doppler effect will be equal and opposite for the 2 beams. And so if you can then come up with some multi-photon trick where your signal depends on interaction with both of these laser beams, there's an opportunity to do that Doppler-free. And finally, you could do laser cooling, which reduces the velocity of the atoms and along with it reduces the spread of velocities. So here's just a kind of classic atomic beam spectroscopy setup. You would have an oven, pass the oven, the atoms that emerge from that through a little hole in the oven, have them go through a slit to help further reduce the angular spread, and then interact with the laser beam here. One challenge is that you can never perfectly collimate an atomic beam, so you'll always have some small spread in angles, but it at least significantly reduces the Doppler broadening. Additional kind of challenge with this is that the atoms are still moving quite fast. Depends, of course, what their temperature was back in that oven. But as they zip across the laser beam, there's a very limited amount of time to interact with the atom. This would lead to a different broadening mechanism, which we would call transit time broadening. It's essentially the Fourier principle. A short interaction time as the atom moves across the beam leads to a broader frequency response. Not a lot of people probably do too much with atomic beams these days, although molecular beams are still quite popular because in some cases there's not an easier really way to interact with molecules besides beams. Vapor cells. In vapor cells, the atoms have no preferred direction. Their average velocity is 0, but there's still, of course, a huge spread, and so the broadening remains. But it is the case that some atoms will happen to transit the beam nearly perpendicular. So if we could find a way to detect a signal that only depended on those atoms that were moving perpendicular, we could have a Doppler-free spectrum. So how do we isolate that velocity class, those few atoms that by luck just happen to be moving across the laser beam? The answer is called saturated absorption spectroscopy. I'll try to describe it to you here in one slide. Saturation occurs when a significant fraction of the atoms are in the excited state. We're picturing a 2-level atom here where the atoms would preferably be in the ground state. But as they start interacting with the laser, if the laser pump is strong enough, a significant fraction of them will spend some amount of time in the excited state. Because of that, stimulated emission starts to play a role, and the rate of stimulated emission becomes comparable to the rate of absorption. The atoms are kind of moving back and forth, right? And the key idea here is that in a saturated vapor, there are fewer ground state atoms to absorb a probe beam, right? Because some of them are in the excited state. But only the atoms that are moving perpendicular will be resonant with both beams. So we've got 2 beams here. One's going to be called the pump beam, and it's quite strong, has enough power to saturate the vapor. And a weaker probe beam comes through perfectly antiparallel. And only those atoms that are moving perpendicular can be resonant because of the Doppler effect. If they're moving at an angle, they'll have different Doppler shifts for the 2 beams, and there's no multi-photon process in that case. And so you can see that here. I just grabbed this image off the web. Here's a Doppler broadened absorption profile. And here it is with the strong pump beam on. You see this spike here. And this spike would, in principle, be limited by the natural line width of the transition. And it's, again, only at 0 velocity. If you wanted to move it to a different velocity class, you could put a frequency shift on one of the 2 laser beams. to extract the signal, there's a common trick that's played, which is called chopping. Let's see if the video here plays. This is just a cell phone picture. So we have a acousto-optic modulator. It doesn't matter if you don't know what that is. Basically, it's a shutter. It's turning on and off the strong pump beam, all while the probe beam is measuring it. And so we see the Doppler broadened peak here, and occasionally we see appearance of these two features. In this case, there are two because this is a lithium atom and it has some hyperfine structure in the ground state. Typically, that chopping would be done very fast, something like 100 kilohertz. For the purposes of that video, I made it 1 hertz just so I could look at it. This was as I was trying to diagnose what had been assembled in the lab that I inherited. I was playing around with it and finally felt like I understood what the chopping was doing. And so what's the point of that? It lets you subtract off. Basically, you can do a subtraction here between the case where you have the strong pump beam and where you don't. And so you're kind of constantly measuring and subtracting the background, measuring and subtracting the background. It's a way of increasing the signal to noise. And you would use a lock-in amplifier to sort of pull out that signal. Additional thing that would be done would be to add modulation sidebands using a frequency modulator, which allows to create a locking signal. That would be this yellow signal here. As you can see, the yellow signal is quite steep right on these two resonances. That's a nice locking signal because it's a very good frequency discriminator. And so you can now feed this into a control system that tries to keep the laser right here. And if the laser drifts a little bit up or a little bit down, it's a very clear change in voltage, and a servo controller can easily push the laser back. Typically with a diode laser, you could feed back either to the laser diode current, which changes the wavelength slightly, or to a piezoelectric transducer, which changes the cavity length and also changes the laser wavelength. The third option I mentioned was laser cooling. Probably a few of you have heard of laser cooling, and a few haven't. And for those of you who haven't, you won't come away understanding it just from this one slide, but I'll do my best. So we all know that light has momentum, right? H bar k. If you were an atom with a mass m, take h bar k over m, and you now have a velocity. So every time an atom absorbs a photon, it recoils a little bit, takes a step back. For a typical case of rubidium at 780 nanometers, that's 6 millimeters per second. That's not a huge amount, particularly if the atom was moving at hundreds of meters per second. But if we can scatter a whole bunch of photons, then in principle the atom could come to rest. And that's exactly what we do. If you take an atomic beam and send a laser beam opposing it in a distance of about this far, you can slow down an atom from a few hundred meters per second to essentially zero. On the bus ride over, I was solving my classical mechanics equation for how much is that acceleration, and it's a few thousand Gs. It's a very large acceleration to slow down that fast. There's a couple tricks you have to play because, of course, as the atom slows down, its velocity changes, so its Doppler shift is changing. So you need to do something else to keep the laser resonant with the atom along the way. That's a detail. Once you've got some atoms slowed down, you can then kind of bombard them from all sides with laser beams, very slightly detuned to the red side. And detuning to the red makes it so that an atom who tries to escape the middle now will see a Doppler shift that preferentially pushes it back. So, for example, this laser beam, if the atom tried to move this way and they were red shifted, but then the Doppler shift pushes it back into resonance, and that beam will move it back to the center. This leads to laser cooling, and okay, I'll show you in a minute a picture of that. Another thing you can do is add a magnetic field, a gradient, which then ties that magneto-optical force, or the force from the laser, to a particular point in space, which will then allow you to trap the atom. So the setup is somewhat complicated, but you have a vacuum chamber and a bunch of laser beams and a bunch of optics. And here's a picture. This is a lithium mott at Bethel. So right here is a cloud of atoms. It's probably something like 1 million atoms at a temperature of about 1 millikelvin. As I said, I inherited that apparatus from a previous professor. I'm still trying to figure out how to make it work precisely. But that's okay. In my PhD days, I was laser cooling ytterbium. here's a picture of a terbium magneto-optical trap with a temperature of about 5 millikelvin, and then a follow-up second stage cooling on a different transition that was to 50 microkelvin. And the temperatures, if you're into low temperature physics, can easily get into the nanokelvins or even below. So I told you about some ways that we have in our lab for making these Doppler-free spectroscopy. And I want to tell you about something else that I've done before. When I was with the Air Force, I was leading the development of a atomic clock that we hoped to put on a satellite that uses a 2-photon transition. So we're back to a vapor cell. Remember last time with vapor cells we were doing this saturated absorption spectroscopy. It took me a little while to tell you about that because I had to explain saturation, and we had to think about how many ground state absorbers, and well, it's slightly complicated, right? Actually, a 2-photon clock is easier. You just have 2 laser beams, and the atom absorbs 1 photon from each beam, and that's kind of the whole story. And if it does that, the Doppler shift is 0, because again, these beams are counterpropagating, the k-vectors are reversed. So you can see the simple math here. In this case, you need the 2 photons to just add up to the total energy that it takes to make the transition, and since the k-vectors are reversed, the shift is 0. And actually, this is better than saturated absorption because for saturated absorption, only those atoms who happened to be crossing the laser beam perpendicular could participate in the signal. For a 2-photon transition, all velocities of atoms can participate. So we can get very large signals. The catch is the atom doesn't really want to do this. So we have to coerce it by using a pretty highly intense laser beam. That's okay, though. Lasers are good. Well, lasers are good at making a lot of power anyway. So we were able to do that. Here's I don't know how well you can see this, but there's a little blue line here, and it's got a little squiggle in it. So that's actually a red laser going through a vapor cell. The reason there's a squiggle is because the vapor cell has a little pinch-off tube there, so there's some refraction. And the reason it's blue is because the rubidium is actually just basically acting as a red to blue converter. It's taking 2 photons from my red laser beam and sending out blue light, enough blue light that you, in this case, can see it with your eye, which is quite a strong signal, or see it with my iPhone camera. And the features that we get here are quite Doppler-free. The width of this feature is about a few hundred kilohertz, which makes actually a pretty nice portable clock. One other research direction that I've pursued in the past is to try to make a vapor cell of calcium and strontium atoms. Calcium and strontium have the right atomic structure for making good atomic clocks, which is, as you've probably figured out, the thing that I've done in the past. But the problem is they have really, really, really low vapor pressure. And so it's a materials challenge to find a way of having some transparent material that could be at 400 to 500 degrees Celsius with a very high density of calcium or strontium alkali atoms interacting with the glass and remain transparent. And we had some progress with it. And if you can see this picture down here, we have a calcium vapor cell inside a vacuum chamber. And we have both red and blue laser beams doing kind of fluorescence spectroscopy here. You can see the signals again with your eye as the atoms emit those colors. So I've reached kind of the end of my time. So I guess I tried to convince you that spectroscopy is powerful and a good teaching tool and generally kind of fun. I ran across this quote. It's anonymous, but it says, "To try to make a model of an atom by studying its spectrum is like trying to make a model of a grand piano by listening to the noise it makes when thrown downstairs." And I don't know, obviously we don't know who said it, but I don't know what particular aspect that person didn't like about spectroscopy, but it could, who knows, maybe it was the Doppler effect. Then if he or she had known about Doppler-free spectroscopy, might have said with Arnold Sommerfeld, "What we are nowadays hearing of the language of spectra is a true music of the spheres in order and harmony that becomes ever more perfect in spite of their manifold variety." So I'll end with that. Thank you.
Okay, the title is kind of impressive there. I've been working with an astronomer, Daniel Apai, over at Stewart Observatory. He has the idea to try to sense if life is present in a distance of about 300 parsecs away from the Earth, which encompasses an estimate of around 1,000 Earth-like systems. So that's the task. And the team is pretty large due to some generous funding by the Gordon and Betty Moore Foundation. We have 4 groups: a design team, fabrication team, metrology team, and mission team. And we're looking at how to do this, starting with a completely new concept of a lens. And the group is international and multi-university, including this university, Ohio State, Korea Basic Science Institute, and MIT, and also some industrial participation from Northrop Grumman. So, how do we sense for life on exoplanets? One way is to image the exoplanet. That's really hard to do. And another way is called a transit study. Now imagine that we don't really image the planet rotating around the star, orbiting the star, directly, but rather we just look at the light from the star, which we can isolate really a lot easier. And we look at what happens when the planet passes in front of the star. In that case, the light from the star will reduce a little bit due to the obscuration of the planet and its atmosphere. Now, if its atmosphere has different molecules like oxygen, ozone, and water vapor, then depending on the wavelength that we're using in our spectroscopy system, we can see a larger dip for molecules that absorb in certain bandwidths. What happens is, as shown in the little animation there, the atmosphere looks larger if there's that component of the atmosphere that we're looking for in that bandwidth. For example, shown here in the near infrared for 3 different wavelengths that some molecule might be present at, for example, ozone here in the atmosphere. So we look at these transitions, these transit dips, to see what the chemical composition is of the planet running in front of the star. I guess if we were looking for alien cows, we would look for methane. That was a joke. So at 300 parsecs, that includes, as I said, about 1,000 Earth-like planets. And for those of you who enjoy the earlier Star Wars movies, I have to correct you that a parsec is a distance. And to give you a sense of scale, the Proxima Centauri, the nearest star to our own, is about 1.3 parsecs. So it's a little over 3 1/3 light years. Now, at 100 parsecs, we can use an 8.5 meter diameter aperture telescope to collect enough light, okay, in terms of photons per second, from a sun-like star to detect these atmospheric components. Now, why do we need photons? Well, the signal we're trying to detect is very small, and it's on a large background. It's on the order of 1 part in 10 to the 6th. And the noise in the signal is proportional, as you know, from photon statistics, right? Proportional to the square root of n, where n is the number of photons collected. So since the signal is proportional to the number of photons collected, the signal to noise is proportional to the square root of n. And the more photons we collect, the more distant systems we can observe. Now, it takes the equivalent of a 50-meter diameter space telescope to collect enough photons to study 1,000 Earth-like systems within 300 parsecs over a mission lifetime, so typically 5 to 10 years. So, what tools do we have? Well, we have the James Webb Space Telescope that's getting ready to be launched. I got to see that last year. It's pretty cool. I could not go into the clean room, but I saw the visitors gallery. It was just so awesome. Collecting area, 33 square meters. if you go through the calculations, the number of habitable planets that we might be able to observe in these transit study spectroscopy measurements over its mission lifetime is 1 to 3, not a very high number. And the maximum distance for life detection is only 14 parsecs. There's a newer system coming on. It's being proposed now and gone through in several different NASA reviews called LUVOIR. And that's got a collecting area of 201 square meters. It's a giant JWST, basically, with a mission lifetime, over its mission lifetime, maybe 30 to 60 planets, or 30 to 60 Earth-like systems, and a maximum distance of about 500 or about 50 parsecs. So what we're proposing is something that we call Nautilus, okay? And it's an ultralight and what I call mode lens I'll describe in a few minutes, completely different concept for a space telescope, and an array of Nautilus individual units, where the lens replaces the mirror, and it's a ultra lightweight transmissive lens. It's in an inflated balloon housing, and that black band that you see is a solar panel. Okay, so the effective collection area for the constellation is about 1,960 square meters, which is 10 times LUVOIR. And the telescopes can be targeted individually or used together for sensing the most distant systems. It turns out to be much more economical and practical than a mirror-based array, given the cost of LUVOIR in the 10 billion range for a single telescope. These details are outlined in terms of cost effectiveness in this article that we wrote in the Astronomical Journal, if you're interested. And I can also talk a little bit about it today. But I want to talk about technology and the optics behind the mode lens. So here's a graphic that shows a comparison of the size of a single mode telescope compared to some devices that you may know about. The one on the upper left is the Hubble, HST. Ariel is, I believe, an EU system for looking at exoplanet transients. JWST there, and the Nautilus array for a single unit, 57 square meters. Now, in order to understand the technology, we have to take a step back and think about how images are formed. Okay, one way to form an image is through a lens. And you probably have had in your physics classes the realization that a lens, a refractive lens, takes rays from an object and bends them through Snell's law at each surface to form light rays at a common focus. Now, the lens material itself changes its refractive index property, which changes the angle of refraction from Snell's law slightly with wavelength. And what that does is shown here. It focuses to different focal lengths with different wavelengths. The blue wavelengths focus closer to the lens than the red wavelength. Okay, that's called focal dispersion. Now, different lenses can be combined into systems, which we're really good at here at this college, used to be a center. And we can make systems with very low focal dispersion. If we don't have any compensation, this dispersion curve, which I'll refer to several times during the talk, is a vertical axis is the wavelength, and the horizontal axis is the focal shift. So short wavelengths focus closer to the lens than longer wavelengths up here. Okay, and the focal curve, dispersion curve, kind of looks like this line. If we add another lens, we can make an achromat, and an achromat has a curve that, instead of being monotonically increasing, has two wavelengths which have zero focal dispersion And the total range here of the focal dispersion is about an order of magnitude less than a system without any compensation. Then we can add another lens or do another trick, and we can make what's called an apochromat, which has 3 corrected wavelengths. And again, another 10x reduction in the focal scale. So we're getting down here into very, very good imaging systems. Okay, very comparable to mirror systems. Okay, now there's something else we need to talk about, which you may not have heard about, and that's a diffractive lens. Okay, and what I'll try to describe in a few minutes is what's called a Fresnel zone plate. So instead of thinking about light as just geometrical rays, we want to think about interference of light. Now you've seen probably the combination of waves into constructive and destructive interference. Like waves in the ocean, when they come together, they make a big peak. That's constructive interference. And destructive interference is where waves combine out of phase and resulting in a zero energy at that point. So in order to think about that, let's consider an aperture. And the aperture is illuminated by a point source. And Huygens tells us that we can consider the light in the aperture as a combination of secondary emitters that each act like a little point source. And the total light at the observation point is a combination of the light from all the emitters. So if two emitters are in phase, they're going to produce a constructive interference at the observation point. And if they're out of phase, then they produce destructive interference at the observation point. And we add up all those emitters to produce the total light level at the observation point. Okay, now we're going to do something. We realize that the constructive and destructive interference properties depend on the path lengths from the source through the aperture second emitter and to the observation point. So we can make a map in this aperture of which emitters are constructively interfering and which are destructively interfering. Problem circularly symmetric, you realize these are rings. Okay, so what we do is we now have a profile view of the system, and we just block the rings that are destructive interference. So what we wind up with at our primary focus point is a constructive, nothing but constructive interference. We have a focus, okay? So this is a focus based completely on diffraction, okay? Or if, you want to think about it, it's really interference. It's just an infinite sum of interference from the secondary emitters. Now, there's also, if you can work through the math, there's also different focal points for this simple kind of an amplitude type zone plate. But the fact is that if we use this, what's called Fresnel zone plate, to block the emitters that produce the destructive interference, we wind up with only constructive interference at the focus point. Now, unfortunately, this diffractive lens is very dispersive with wavelength, okay? And I call that diffractive focal dispersion. We'll talk more about that in just a minute. One of the things I wanted to say is that we can actually improve that transmission efficiency. Instead of blocking some of those zones, we can make what's called a smooth zone diffractive Fresnel lens that has the same diffractive property, only it's a lot more efficient and all the light gets into that first order focus. The way we do that is to think about taking a lens of the equivalent focal length, a simple convex plano lens, and take out of that lens ambiguous sections of one optical path, one wavelength of optical path difference. Okay, and when we take that lens and remove those ambiguous sections, remember light is a wave, so it's harmonic over a wavelength, then we have what we call a diffractive Fresnel lens. And it has the same diffractive focal dispersion as a zone plate, but a clear optical path. Now, there has been a lot of work done on making huge diffractive Fresnel lens. This one is at Lawrence Livermore, 5 meters in diameter. And with the application to space telescopes. This concept at Lawrence Livermore was called eyeglass, and Ball Aerospace had something called the Moray program. And the idea here was to make Gossamer-type telescopes of this 30 to 50 meter diameter aperture. They're very large aperture. They're ultra lightweight. There's no central obscuration. And it's got 4 to 10 times better fabrication tolerances than mirrors. Okay, let's look at some pros and cons. Okay, refractive lens, diffractive lens, and mirrors. Launch mass, refractive lens, very high. Diffractive lens, very low. Mirror, very high. You've got to have a very stable substrate and all sorts of things in the back of it. Focal dispersion, refractive lens, pretty good. Diffractive lens, not good, okay? Mirror, excellent. Alignment sensitivity, fairly easy to align a refractive lens and a diffractive lens. Very, very difficult for a mirror. That's one of the big problems with mirrors. And with the optical paths, refractive lens, clear optical path, diffractive lens, clear optical path, and that's with the diffractive Fresnel lens I described. In a mirror, you always have an obscured system because you've always got a secondary mirror, okay, here, in simple systems. So now, what we've done with the diffractive Fresnel lens is make this very thin, very lightweight system with one optical path difference, one wavelength of optical path difference, surface features. We can do something else. We can make what's called a multiple order diffractive lens by removing not just one wavelength of optical path difference, but a factor of m waves of optical path difference in a similar sort of way. So this is a lens that is kind of a hybrid between a refractive lens and a diffractive lens, and they both have some very interesting properties. If you look at the relationship between a DFL and a mod lens, the mod lens is slightly thicker, although really not that thick, and the zones are spaced more widely apart. Now in this animation, what I'm going to show is the focal region due to a mod lens with different M numbers. So the first line here is a classic diffractive Fresnel lens, and then as I increase the M number, what I'm doing is increasing that height of the transition in the diffractive structure. And I've graphed 5 different animations for the same focal area, where this horizontal axis is just the region around focus, and the vertical axis is the vertical axis Y here, about 40 microns or so for these parameters. And what I'm going to do is show an animation versus wavelength as the wavelength increases. To start out at the design wavelength, all the focal spots are in the same spot. And as I, hold on a sec, increase the wavelength, unlike a refractive lens, the diffractive lens with the DFL, the focal spot just goes right toward the lens. And the maximum range of the simulation here is starting over every once in a while, so this is now starting over at the design wavelength. As I increase the M number, something very interesting happens. Instead of acting like a diffractive Fresnel lens, the focal dispersion range decreases as the M number increases. So that gives us a system that's very close to a refractive lens, but in a much lighter and thinner geometry. Okay, and what we've done on top of that is realize that we need to treat the back surface of the lens in order to compensate for both refractive and diffractive dispersion to get the minimum focal shift with wavelength as possible. We call that the multiple ordered engineered surface lens. The engineered surface comes from the back side where we put on the DFL on the back. And this isn't limited to just a diffractive Fresnel lens. We could, for example, incorporate a simple grating here to make a single lens achromatic spectrometer. Okay. We could also use other types of engineered surfaces to produce other sorts of work functions for the optical system in a single ultra-lightweight component. Okay, so here's some real mode lens designs, B through D. These are things actually being considered for fabrication right now. Compared to a classical achromat of the same size, that's about 24 centimeters in diameter. And it turns out that the mode designs perform significantly better than the achromat. Even the best achromat that you can design. We're much, much better performance than that. And I understand that after our group photo here, the demo's set up due to, thank you, Daewoo Kim's group and his people. And so what you'll see in the lobby is a much larger diameter mode lens. I think that's the same 24 centimeter diameter lens. This is diamond turned out of plastic, but it's the same size that we're making for the Moore Foundation. And actually we made a telescope. This is the world's first functioning mode lens telescope. It's kind of small, okay. But you're free to come up and look at it. It's got a mode lens in the front of it. That's the only lens in the system, and a simple Thorlabs camera. Okay. And we took several pictures with this thing. We got up on the 8th floor. If you've been up to the patio, it's beautiful up there. And looked across campus to Old Main. It was kind of a windy day, so actually I think we were limited by more by the atmospheric turbulence than by the optical resolution. But a nice picture of Old Main there. And got to take a picture of the moon. And there's the U of A Student Union. This is the focal dispersion curve that's measured. Okay. The curve that's going up like this, remember this is focal change position, this is wavelength, is that classical single element curve here, and that's for the mod surface without the diffractive Fresnel lens corrector. When we add in that diffractive Fresnel lens corrector, we now have an achromatic system that doesn't change focal length very much over wavelength. The dotted line is if we were to use just a single order diffractive Fresnel lens. And you can see that just a small change in wavelength changes the focus a lot, and it just doesn't work. That was the Moray and the eyeglass systems, and we're proposing this system. The performance was pretty good. We got this is an image off the camera. These are the profiles, X and Y. A little bit of asymmetry here due to my student and I taking a screwdriver and a hammer to get the diffractive Fresnel lens debonded from the mold. We've improved our technique since then. And then there's the airy spot diameters. Pretty good, pretty darn good performance. Okay, and if we look at that image of Old Main, this is no image processing. Distance about ½ kilometer, at the diffraction limited resolution of about 1,000th of a degree, and that's the same as the pixel spacing. So we never expect to get actual image resolution that good. Okay, but there's a student evidently carrying a cell phone or something with a backpack, and this is a plaque there by Old Main. I'm not sure what it's some sort of a historical group of plaques of names of people. Does anybody remember what that is? Anyway. So student's head, standard student head diameter, okay, in degrees is about 0.023 degrees. And you can definitely see there's her eyes, her nose, her mouth. So our resolution is much, much better. I don't know if it's a factor of 10 better, but it's pretty good. Okay.
There is life on campus.
Pardon me?
There is life on campus.
Well, if you call students alive. They're alive in my class. I don't know about yours, Miss Sarah. Okay. Now, the next trick, which I can't show you because we haven't submitted the intellectual property yet, but we can color correct this completely, okay, to make essentially true diffraction limited system in these big diameters. Okay, and that's a little simulation showing what happens with different wavelengths, and then the composite there is in the lower right. Okay, so what differentiates mode lens technology? Unobscured transmission, 4x improvement in fabrication tolerances, and 100x improvement in alignment compared to mirrors. Ultra lightweight, at least 10 times conservatively than a mirror. Short focal length, reasonable spectral response, color compensation can produce diffraction limited imaging, and we're gluttons for punishment. We're actually replicating these things in molded glass. Okay, so it's cheap. Well, not the first one. So where are we headed? Well, our current plans are to develop theory, design, simulation for mode lenses. We've come a long, long way with that. We're developing, actually, I didn't realize this when we started, but we really are doing state-of-the-art glass molding technology, okay, for mode lenses. These have, the ones that we're making now are 50-to-1 aspect ratio, and the larger ones will even be larger aspect ratio. We're developing these very cool deflectometry testing techniques in Daewoo's group for the alignment of the lens segments. We can't mold the whole lens in one shot because just the molding machine is too small. That's just engineering to make a larger machine, but they didn't give us money for that. Deflectometry is so cool. They use the largest televisions that are made in their deflectometry setups. If you look at the one downstairs, it's 82-inch diagonal. So I think that they just like to play video games. I don't know. Okay. So we're fabricating this with this 24 centimeter diameter aperture mode telescope based on a low temperature LBSL7 glass with a color corrector. And our goal is to demonstrate on-sky experiments at Mount Bigelow, Arizona, the observatory there by December of this year. You might imagine other applications. Well, of course, you know, lightweight drones, lightweight security monitoring, short pulse laser systems. You know, there's probably some nonlinear talks that you heard today. One of the problems that they have with their optical systems is that the more glass they go through, the more dispersive the system is, and that could broaden their pulse width. Okay. Well, if you have less glass, you have less dispersion. So their pulse front, that they call it, could now be aligned with their wave front, okay, which is kind of cool and eliminate some problems for those guys. And also, I mean, you can bang these things out like optical data storage disks, right? Okay, so to make cheap, large solar collectors would be also, I think, an enterprise level application. Okay, so with that, I want to thank you, and I've taken a little bit too much time, but pretty close to noon. Thank you very much.